there's a chapter, an IPython notebook, which is much more detailed explanation of kind of my research into this area. So I've put that on the web. It reads kind of like a book chapter. I was going to originally write a book with this as an inclusion. So I did that. I've been inspired by the Bayesian hackers, Bayesian for hackers, the Cam Davidson Pilon. He pushed out his sort of book as a GitHub repository, and it's brilliant because it's just an IPython notebook, and he hasn't made any sort of play that he's going to actually put it out as a book. But it's a great idea just to push out IPython notebooks, because obviously everybody knows what IPython notebook. Everybody there with that, we're all okay. We all understand that. So what I've got is I've got an IPython notebook which you can put as a gist, and you can stick on GitHub, and then it just comes as a static document. So I've linked from my website to that. I've got a live document, an IPython notebook, that covers this as a kind of chapter, a bit more detailed. And what I've done now is I've pulled off the what I see as the kind of meat of what we need to talk about today. So I've been through this once before. It takes about 45 minutes. So what I've done as well is this is a IPython notebook that's been transformed using the IPython notebook slideshow. It gets longer. They put more things on the end of it. And so that's available as both an IPython notebook and as HTML. So that's everything covered. So it's like you've got a lot of take-home with this particular discussion. So the only thing is, I just have to keep my eye on, nobody can see this bottom corner, but this is the kind of controller. So I have to sort of bend over and control it this way. So my name's Jonathan Edwards, Jonny Edwards. I've got a small consultancy in Newcastle. If you don't know where that is, it's a long way that way, just near the borders of Scotland. And I've been doing bits and bobs around data science and machine learning for the past, well, the business has been going a couple of years. So I was interested initially in recommender systems, not from we'll talk about the idea of users and items, which is the predominant sort of area for recommender systems. That's not what I was doing to start with. I was actually looking at proteins and compounds, so how you might get proteins and compounds to kind of, how you might build a matrix of proteins and compounds, and how you might infer activity between compounds and proteins. So my data, actually the little bit of data that you'll see that I've graphed up is actually a little portion of a protein compound matrix, an interaction matrix. So I did that work, and then I kind of wanted to take a step back and wanted to fill in a few gaps in my own understanding about some of the different techniques, because there seems to be kind of nomenclature problems in this area. People call SVD one thing, there's SVD++, there's all kinds of different things. I wanted to sort of like, collaborative filtering gets used as a kind of whole terminology when I kind of see it as a little bit. So I want to kind of put my own sort of classification on the techniques, and what I want to do is really classify them in terms of the principles they use, rather than specifically the names of the techniques. So what I'm hoping, it's a novice level talk. I'm hoping to give you an understanding of the problem of making a recommender system. I want to give you a headline as to the kind of guiding approaches, and then we're going to look at some Python. There's not actually much. There's a small bit of numpy, which is the only real bit of code that I've written. The rest of it is really libraries, and that's the great thing about Python is it's normally been done before by somebody who knows about it a lot better than you. So, and then there's a few shortcomings to these approaches, which people don't often sort of tout about. They sort of keep that to themselves, really. And I don't want you to go away thinking that the recommender systems is a kind of solved problem, and you don't need to do anything. You just need to fire up some code, and that's it. But what I want you to go away with is a set of tools that if you are going to approach this problem, you know how to do it, and you know some of the ins and outs of some of the variables. One thing I try and drives all of my work is the idea of do things seem sensible? So when we look at the data, I urge you to look and say, well, do those numbers seem right? Do they seem something that I can understand? So that's that. So if you want to follow this, these are the libraries that I pull in. Most of them are in the, whatever it's called, Anaconda. But NPL tools and nimfa and sparsesvd, they're not there. So I pulled everything in via pip, which probably means my machine is infected by, I don't know, there was that pip thing, wasn't there? About 6 months ago. I don't know, do people know that? Do you know about that?
Is the logbook available somewhere?
Yeah, everything's on my website, but I'll put it on GitHub as well. Thoughtfultech.co.uk. So it's all linked up. So what's the problem that we're trying to do? We're in the sort of traditional setting, we're trying to look at what users do and look at what items do. So the traditional setting for this is something like Amazon. So if you've all seen the recommender kind of bar of Amazon that said people who bought this do this, and companies are interested in that because it affects the margins, and they want to be able to make good judgments because they don't want to email people kind of wrongly chosen items or email the wrong person. So the idea is to try to understand the underlying purchasing behaviour of the customers they've got. And by purchasing behaviour, I also mean the underlying properties of the items that they've got as well. So we're kind of trying to figure out what we're going to do with items and with users. Again, I've written it here. So we can recommend products, and so we can look at maybe stock levels. There's a whole host of things you can do once you've got this idea. So the best way of thinking about this and the kind of guiding sort of structure for all of this is a matrix. And the type of matrix we have is this. So this is my family. They're my family. And these are what they do. They drink ginger beer and lemonade, and occasionally we drink a lot of champagne in our house, which is really nice. So this is a user item matrix. So my sister Julie has bought 3 bars of chocolate, and my daughter Rosa, who's 10, has drunk 6 bottles of champagne. So that's the kind of matrix. And you'll notice that there are these blanks. I haven't put zeros in deliberately. We've got kind of blanks where we don't know what's going to happen. We don't know. People haven't done anything. So we don't know. So they're up for grabs. They're the areas that we need to look at. One thing to do, well, I'll show you this first. So we can boil this down into kind of an interaction matrix. We've interacted, these 2 products have interacted, this person and this product have interacted, sorry. And that's just a binary version of that. So what was I going to say? So yeah, so we've got this matrix, and we've got this idea that, so one thing to do now, this is what I was going to say, one thing to do now is to just look and say, right, what would I do? If I was having to do this as a day job, and somebody was giving me a matrix and saying, where should we send our emails? Where would I send my emails? And I sort of think, well, Karen looks a little bit like she is reluctant, but she's bought a little bit, but everybody else has bought all of these products. So to my mind, there's a sort of gap here where you think, maybe people are going to do that. And these products look like they're selling. Maybe this person isn't a buyer. So this is the sort of game that one plays with recommender systems. This idea of users and items, and whether they've got a propensity to buy or whether the items have got a propensity to sell. So certainly, this item here, this person here is a heavy buyer. Ruby, my little daughter, she's a heavy buyer. And these products are heavy sellers. So it sort of stands to reason to sort of, to my mind, they're the key areas that when we do some analysis, we look at, and we can gain some assurance by looking at those and say, oh yeah, it's doing something that I think is sensible. So that's the matrix. So that's at the start. That just pulls everything in. And there's 2 approaches. There's 2 kind of principles. There's many approaches, but there's 2 principles. So the first principle is we kind of do some kind of averaging along the axes. So we sort of say, do you know what? This person's a bit like that group, therefore they might do this. So it's trying to sort of take the group behavior. Is we know what's similar about somebody, so we know that if somebody's similar to somebody else, then the chances are the difference is going to be something that we can work with. So again, we can do that with products as well. We can look at how similar products are and whether they're selling or not selling, and whether they sell to. So that's the idea. So we're kind of taking the matrix. If I go back a slide. We're sort of saying on a row by row basis, and we're sort of saying on a column by column basis. Okay. So the second idea is a little more sort of statistical and a little more, I would say, what's the best way of putting it? It's a little more sort of process oriented. And that's the idea of a factor model. So the idea that you've got a latent factor. So the idea that underlying this data is some kind of decomposition that drives the underlying activity of people and the underlying activity of items. So there are techniques for both of these. There are techniques for collaborative filtering, and I'm just demonstrating a really simple one today. The latent factor matrices ideas, the non-negative matrix factorisation and the singular value decomposition. They're the business in Python. You'll see you can do it, and you can do sparse versions, and there's 4 libraries for it. Again, not linked from Anaconda, but readily available via pip. And you're in a great world as Python users to do that kind of work. So let's look at this idea of aggregation. So what we're going to do is we're going to take the k nearest users. We're going to look down the user list all across the items. Should have put users items. And we're going to look down the user list, and we're going to sort of aggregate them into similar sort of sets. And then we're going to calculate a new vector based on this aggregation function. So we're going to take them, we're going to find out what's close. And by close, we have a k value. You'll see that a lot of these techniques have k values. Does everybody know what I mean by a k value? An initialization variable that you have to fiddle with to get the thing working. Underlying this is the concept of distance and the concept of things being together and being able to figure out what distance between things means. And I've just taken a simple Jacquard distance measurement here. If anybody's ever kind of touched it, it's the 1 minus the intersect over the union. So in this case, we've got kind of 10 as the union, and then we've got intersections of 5 ones. So that's the Jacquard measure. So you can use arbitrary measures. The idea of collaborative filtering is quite general. If you look particularly on Wikipedia, it gives you a general sort of algorithm, and there's lots of tuning that can be done around this particular approach. Fortunately for you guys, a lot of the methods are really easy to implement in NumPy and are very available in SciPy. So this is that's all the code that you need to do a collaborative filtering on users. It falls out really nicely, and this is what you start with. Initially we're looking at binary data. I tend to focus on making predictions about where you're going to find people rather than how much they're going to buy. Mainly because that's the background in sort of protein compound interaction that I came from. But so that's the code. This is the matrix that we started with. This is our prediction matrix. So this is x dash. So we'll see that it's not a million miles different. We're actually making some 0 predictions. We're making, where are we? We're actually sort of changing that one. And we're making a prediction around the Ruby one here. So we're not doing a massive amount on this one, but we're making a few odd predictions. Now, one thing you'll notice is some of the ones have been made into 0s. So we're actually saying we don't think somebody's going to be there. We don't think there's going to be a sale there. So that's interesting. What do you do when you've got data that tells you something that your model doesn't predict? Well, in our approaches, we always said data trumps model. So that was the way it was. So we have the data trumps model idea. So that code, all it did was it took the matrix, it took distances between, Jacquard distances between, I'll go back actually, because I haven't explained that thoroughly enough. So we took Jacquard distances for each one of these down in a group of 3, because k equals 3, and then we aggregated those groups. And then we replaced the value with that aggregate value. Okay, so does that make sense? What do we feel about that results? Well, the idea that a model is predicting something that the data tells us differently is not great. We don't like to see that. We like to see models predicting data that we already know about. We like to see that. We don't like that not happening. That's not good. Obviously, there's a lot of tuning that can go in. I didn't want to tune. I didn't want to present something. I wanted to present you with techniques that are kind of warts and all. So I didn't want to tune it. And the easy way to do this the other way around is just to flip the matrix. So what do we feel about collaborative filtering? Well, those results aren't great. The idea seems interesting. The idea seems something that we can get our head around, maybe something we can explain to our bosses should we have to justify what we're doing. But we'll see. There's other ways of doing this. So is everybody familiar with the idea of a latent model? Have we all got that background in our heads? We all understand what that means. Hands up if you know. No, right. So the idea of latent models is the idea that with any bit of data, there is something underlying driving it. So there's something behind the scenes that actually we're better off looking at. We're better off looking at it because it's normally smaller, and it's normally more demonstrative of the data. So it's less. It's a compression. It's more of the data. There's less. Is there less entropy? Oh, the same amount of entropy, but so there's less there to play with, and we're trying to get at this underlying driving force. So here's an example that I use in the book. The idea that you might represent a music band by the year, the band name, the album name, the sales, and a rating. So we can already see, well, the band name, the album name doesn't really mean anything. It's actually sort of somewhat superfluous. So we've already got some data that we've kind of got a bit of redundancy with. So when I bought records, when I was a grunge guy in 1991, I'm probably showing my age now. When I bought records, you know, it was grunge, and that's what I was buying. I was in the 90s, and I was buying Nirvana and Pearl Jam and things like that. So, so this data, the Nevermind album, which sold 30 million copies, and I guessed this. I guessed that number, which was amazing, and then looked it up on Wikipedia, and I got it right. So that's really good. So that number, underlying number, doesn't actually mean a lot. All that I was really interested in was this idea that it's a 90s grunge band. And I'm probably still this. I've been through dance and I'm back into grunge. That's my little journey in music. I went through dance and out. So at one point it was 90s dance, and then it was back into grunge as I got older and a bit more sort of stayed in my ways. But they're the latent factors. It's a really interesting thing. It's a really interesting idea. What is it behind the data? Now the problem with this description is we've got names for them. We know what they are. We go, yeah, that's your latent model. And that's the problem with latent models, is there's not often a set of names. There's not often a way of showing somebody, saying, do you know what? We've found out that people buy roses on Valentine's Day, you know, or something like that. There's not often that kind of nice description. Oh, the model, this is what happened. It often doesn't happen, and lots of latent models are set up so that it's actually quite complicated to get back to that. So we don't know what's going on. And indeed, you'll see with these, we just have an arbitrary bunch of numbers. So this idea of latent models is not without its weaknesses. It'd be nice to have some technique that got you the latent model and explained it all for you. That would be lovely. Somebody needs to work on that one. But there's this whole issue of causality and all the kind of things that statisticians get quite keen about. But what we're trying to do in this next set is try and figure out latent models. So there's two techniques. There's more than two techniques, but there's two techniques that are readily available in Python and interesting. One of the ideas is to use a matrix. We've got a matrix of data, so we're going to use a matrix decomposition. And we use a decomposition of the dot product. All that means is we're kind of linearly, because the dot product is the addition of the multiplication, then we're just linearly sort of modeling this thing. And we're taking a set of data for the users and a set of data for the items, and we're saying, how can we model those two things? How can we have two matrices that are sub-matrices of our big matrix that we multiply together, forming our big matrix? How can we get two really small versions of those that really encapsulate all there is to know about the data? So that's what happens with a non-negative matrix factorisation. You do a decomposition down into two matrices. There are lots of things to do with the formation of these matrices, and there are lots of methods. I think in the nimfa library that I linked to in this talk, there's 10 methods. There's probabilistic methods, there's Bayesian methods. It's been around, it's fairly mature sort of technique. Although interestingly, not the machine learning guys, like Murphy, the people who publish the big probabilistic books, they tend to give it quite short shrift actually. There'll be a big chapter on topic modelling, but then this is, this is often quite a small sort of aside. I don't know whether they don't like the idea or we'll see there's one reason why you might not like the idea, but so note that we pick a k again. So we normally pick the same, well obviously we pick the same size k, so we're trying to make them smaller, and we're trying to make this k small such that it represents the data, but it doesn't totally represent. It's not totally. There is some compression going on. So how do we find UMV, and then what do we do once we've got that? Well, the best way is there are several techniques. They're all optimization based or sampling based. And they're all, a lot of them, like I say, are implemented in nimfa. And it's an iterative optimization problem. We try to optimize. We know some gradients, so we know directions to head down. There are various discussions about which is the better method. But nimfa implements them all, and it implements a binary version as well, which is really good. The best page, which is linked to here, it gives you a very good explanation of the iterative optimization. Very, very good explanation. So let's get on with the code. So we've got the nimfa library. It's not a readily well-known library. I don't imagine has anybody ever heard of that library before here? It did come out of a summer of code type situation, and it came out of academia. So it's not a commercial library. It's open source, and it's not readily linked to. But to my mind, there are some matrix factorisation methods in scikit-learn. But I've decided, because I wanted a rounder sort of version of it, was to stick with the nimfa library. There's extensive documentation, and the guys have done a really good job there. Well done for that. So all we do is we run a method, we give it a rank, we have some iterative method, and maybe 1,000 is too high, and then we iterate around, and again we're not getting massive changes, but you'll see we're making some predictions where data isn't. We're making that's the one that you've kind of bought a lot here. You've bought a lot here, so that one seems like a sensible prediction. The other predicted area is here. We've got a one here. Is there any in the middle? I reran this, so we've got some difference here. Oh no, we've got a 1 there. So we're making these specific predictions about areas that we see that we can sell to. So what we would do as a website or whatever is we would target those customers. Okay, so the code is really simple. The only thing is we have a slightly strange nomenclature for the two latent matrices. So that's fine. We make a prediction that way. So that's matrix factorisation. There is a binary matrix factorisation as well, BMF, and we iterate less on that. And again, we're making some prediction. We're actually not making. So I don't think I've optimized this one. I think I need a bigger rank to make some better positions. But what I wanted to highlight is there is this little game that you play with the k value. That's what I said earlier, was this idea of a k value and this idea of setting it such that you don't reproduce the matrix totally, but you don't kind of destroy it and not return anything that you know is right. So you want to produce all of your data, make some predictions, and but not kind of destroy, make the latent model so small that you're not making anything sensible. There's nothing there, basically. So again, this is the nimfa method, and we pull this in, and it's fairly straightforward to implement. So that's 3 methods we've done already. So if somebody comes to you and say, I want to recommend a system, what I want you to go away from this talk with is to say, I can do that. You know, I can have a first stab at that without a lot of hassle, to be honest. Just getting the data in that right matrix format is a good starting point. So we've covered collaborative filtering. We've covered the couple of matrix factorisation techniques. The binary method produces a specific binary factorisation. So it uses a slightly different optimization algorithm. Okay, so here's the one. So I'm left thinking, I'm not sure about this, and that's the way I looked at this data. I was left thinking, I don't really know what K is, and I don't like that. I don't like to sort of have to guess K. I like to have to know a bit more about things, because this K, how does it affect? In this case, it affects it quite heavily because the matrix is very small. But on bigger matrices, you know, what do I need? Do I need K of 327? Do I need? If anybody remembers the old neural network days when people were building hidden layers and not knowing how many nodes to put in a hidden layer, you know, there was always that kind of discussion about these K values, and anybody who's ever done K means will know exactly the same. You know, you're always sort of guessing. I know there are ways out of that now. In fact, there is a probabilistic method for this, which I think uses sampling, and I think builds K, integrates out K as a kind of nuisance parameter. But I haven't looked at those in detail, and I think they're quite timely for large matrices. This is a kind of quick and dirty approach. So some easy questions. Do the results look sensible? Well, I'm still worried that I'm not getting back what I've put in. How well does it scale? You'll see in my notes that this technique doesn't scale as well as the next technique we're going to talk about. Is the answer unique? No, it's not. So the U and V matrices can be significantly different and produce the same results. There's no unique U and V, which to my mind is a worry. And what about this initialization value rank? What can I do about that? Well, I could take a Bayesian approach and integrate it out using sampling, or, you know, we're back to the kind of guesswork world of sort of data science, guessing what we're doing. Okay. So here's my, if I'm running this as a horse race, singular value decomposition is my front runner. It's again a factorization. It's a special factorization that allows for a kind of a scaling, a rotation, a scaling, and a rotation. The middle matrix gives you some kind of feel for how much value there is in keeping a matrix of that size. So it extends out, which is really, really important, because once I know roughly what K's doing, K being the size of this diagonal, then I can make some better predictions. I can use, this technique is also analytic, so I get the same results every time, I think. And everybody knows it, and it's been around since, I don't know when the first SVD was, probably about 1830 or something like that. It's a very old mathematical technique. It's one of those techniques that people just, when they get data, oh, let's just throw it at SVD and see what happens. It's just one of those kind of do-all kind of techniques. Has everybody heard of SVD, or is it a new idea to a lot of people? A new idea, right. It gets latent semantic indexing. Has everybody heard of latent semantic indexing? No. Well, it's the same similar sort of approach. You have a bigger matrix. But I urge you, if you're doing this kind of recommender, get into this idea of the singular value decomposition. It's got a lot of grounding, and you'll see there were guys taking it a lot further in the last 5 or 6 years. There are people really stepping up and taking it even further. So it's a really sort of powerful technique. And the one important thing, the one thing that I really like, because I like plots, is it gives you something called the elbow plot. So we'll run through this, and I'll show you what an elbow plot is. So an elbow plot is kind of like the power at different Ks, right? So it gives you how much power you've got to represent your matrix at a different level. So you can always plot this. In this case, everything can be represented quite easily around the kind of 2 to 3 mark. It's called the elbow plot because if anybody's done PCA, it's a similar sort of thing. You look at where there is this turning point, and that gives you some indication of where your data is, kind of where the power of the data is, where the actual data is and where it isn't. So the elbow plot is really useful for plotting that and for showing you roughly what you should be. So to me, that gives it a tick in its box. That's kind of, you know, that makes it a more powerful technique because you've got this kind of windowing on it, windowing on what's happening. So again, It's a really easy call. The SVD library is available in scipy. There are numerous SVD libraries available. I think at my last count there's kind of 6. There are sparse versions. There are 4 sparse versions, I think. There is ProPack. There is SparsesvD. There is another one that I can't remember the name of. But there are lots out there, and they're all implemented in. They're not implemented in Python. They're normally linking up to a lib, where somebody's done like libsvm, somebody's done lib sparsesvd. So a really kind of assured bit of coding. The SVD in scipy links to LAPACK or BLAS, or both actually, something like that. So these are really solid bits of code. You're not going to really do a lot better than that if you implement them yourself. You're not going to beat BLAS and LAPACK. They've been around for 20, 30 years, people optimizing those out. So that's the great thing about Python is a lot of these old C libraries are getting pulled in, and you're getting access to the proper tools. It's not like you're prototyping. You can actually start building proper systems. So let's look at the production. So this to me makes a lot more sense. Can everybody see this? I'll put it a bit higher. So I think my K was 2, and I'm making some. I'm still sort of off, but I'm being a bit more accurate. I've made a whole bunch of predictions here that I didn't make in any other methods, but that was the kind of line that we were interested in. We were interested in predicting this bottom one, and we're not saying they're going to perhaps buy as many as the full set, but we're certainly saying she might buy 1. So we're making that good prediction, and this seems more sensible. It seems on small data where you're able to eyeball it, it seems to make more sense. So I'm sort of happier with this technique on lots of levels. I'm happier with it because it seems to do something more intelligent. I'm happier with it because I've got the box plot, the elbow plot, and I'm happier with it because I can shell out to ProPack and I can get it done in seconds. And I can represent this as a sparse version, and I can do good things that way. So I'm a lot happier with this technique. So do the results look sensible? Well, to my mind, having looked at a lot of sets of results like this, yes, they do. Does it scale? Yes, it does. Is the answer unique? Yes, I think it is. I think it is. Pretty certain it is. And do I worry about this initialization value, this rank value? Well, not so much, because I've got the elbow plot. So it ticks a lot of the boxes. So if I was to say to you guys, you've got a day to implement one of these, you've got some data, SVD, first port of call, see what happens. Okay, so one issue that we sort of have a sort of subjective view of the data. So how do I know how well something is doing, given that I don't know the results that I'm supposed to be getting? Now, this is a big question in the recommended community. And in fact, it's been on Quora, and everybody says, how do I assess? Because the key thing is, if you've got some predictions that you've made, so you've got that matrix and you've got values in it, and you say, oh, yeah, I can do really well at those values. Actually, you could do that in a binary setting with a completely full matrix of 1s. You could guess everything right by just guessing everything. So there's this idea that it's actually quite hard to judge whether these systems are working or not, because the latent model, you don't know what's happening. You don't really know what's happening with the zeros because they're zeros. So you don't know how to treat them. You don't know whether to treat them as a single zero or whether to treat them as a kind of an NA, something that I haven't made a prediction for. So it's an interesting little... It's an interesting little idea. I was running my recommender against another guy who he had a system that just over-predicted. He had this Bayesian system that over-predicted, and it really annoyed me because he would get really good results because he was just predicting everything, and he wasn't worried about whether we were just using RMS on the individual values, and he was not playing ball in my eyes. So I invented it. So to beat that. Rather cheekily, I invented another RMS that took some of the zeros. So this is the RMS of all the places where it's 1 in a binary matrix. So we just take RMS there. And then we've got this idea that some of the zeros might actually be zeros. So let's just arbitrarily take a bunch of those. These matrices that we were dealing with were 1,000,000 by 60,000. So arbitrarily take a bunch of, and they were very sparse, so I'm not taking a lot of zeros. So arbitrarily take that bunch. So I invented this sort of hack of a an RMS measure that allowed me to kind of beat him at his own game. So instead of getting better techniques, what I did was move the goalposts. So that was quite good. But in all seriousness, the idea of judging whether a recommender system is working or not it's not something that the community. The guy on Quora said, do A/B testing, which implies that you've kind of built it, you stick it in front of a set of users, you see whether the users are, so there was this idea of actually running the whole system and then figuring out what it's gone, which I thought was a little bit sort of far down the line. So what we've got is we've got 3 techniques so far. We've got two principles and 3 techniques that we can use. We've got the collaborative filtering models. We've got the non-negative matrix factorisation, and we've got this SVD. So what I've done is I've taken one from each side. I've taken the item by item collaborative filtering, and I've taken the SVD and run them against each other on some data that's available on my website. And the way I like to do this is with the data is to do it as an image. So if you've got big chunks of data, you don't want to be looking at the numbers. You actually want to be looking at images. So what I've done is I take one image and I flip some bits that I know are right. So if you look at that line there, I've got rid of all of that line virtually. So I just wrote a little vectorized little flipper that flips a few bits and gets rid of a few of those. So I know the data's there. I knew the data was there originally. I'm getting rid of it to run some kind of test on. My idea is, again, what is sensible? It'd be great if I could fill in that little line there and make those predictions again. So that idea would be really powerful. And you can see that these areas are less, I don't know, maybe less sparse. I've not flipped a lot of ones, but... So that's that. So what I'm going to do is I'm going to run this. We're going to look at the images, and we're going to look at the RMS values, and we're going to see what happens. Obviously, so there we go. So one thing is, you can see how there's kind of homogeneity in this. So because I'm kind of averaging things, we get a more homogeneous sort of set of data. I've sort of made a few predictions here. And my RMS, if you just remember these numbers, is 0.14 and 0.48 for the sampled RMS. I think it's that way around. So what we're doing is we're trying to fill these lines in, really. So let's look at that. Let's look at our second technique, which is SVD. We've got an elbow plot. And we look, and I should have put the two next to each other, but we'll notice that this line is a lot stronger. So we've made some predictions. So that's quite sort of magical, really. We're sort of making predictions that we know are right, but we haven't got the data there to start with. We've used a latent model. We've arbitrarily picked a K. And yet we've got some results. It's quite good, that. It's quite a good sort of setup. You can always find that. If you're doing any kind of machine learning, if you can kind of get a result by just hacking a few bits together, then you know that you're on to doing a really good thing once you start really concentrating on what you're doing. It seems to me, if I run a project and something doesn't look like it's going to go right from the start, i.e. I've had to really fiddle things, I've had to fiddle K, gosh, it's so sensitive, then you know you're on a loser once you try and tune it for real commercial implementation. So both these scores are very significantly down on SVD. Now I'm not being fair here, because this SVD is a real kind of production system. You would implement this. The collaborative filtering method, firstly, it would be slow, and secondly, you would probably look at more sophisticated sort of aggregation functions. But then again, I'm pretty close with a good K value. So, yeah, okay. So this is what you do to build one of these systems. You collect that matrix, you choose your algorithm, you build your prototype, you optimize performance, and then you do the view. So it's really simple. The one problem you have, and the one problem I find, was this update cycle. Because I'm getting new data in. I'm getting new data into the system. When do I update it? I've got to run the model again. And particularly if it's something that takes, you're getting data every week and the model takes a week to run. One implementation of this I had took 2 weeks to run. So that was on a very big non-sparse matrix. So that's an issue. But with sparsesvd, you're not in that little space because you've got, I can do big matrices in seconds, providing they're fairly sparse. So you've got, the one thing I would say is this idea of the update policy is make sure you know what you're doing, when your data, does data trump model, and when does that all happen. Okay, so looks like magic. That result that we got with that data where we filled in the line, we had no prior knowledge about that line. It's good. It's clever. We would have sent the right emails to the right people. But there's sort of a magic. There's a magic to both approaches. This idea of latent models is always been one of those things in statistician circles that they sort of talk about whether there's causality in all the issues associated with sort of underlying models. There is one thing that you should be aware of. You need a lot of data. So the more data, obviously, the more data you have, the better the results you're going to get, because the more kind of rank, the more power you've got in your data set. So that was that sort of thing, and this whole matrix thing is being played out in something called the compressed sensing community, which is this big idea that people have got about, instead of sensing full data sets, we actually do something clever and we subset a full sense. The example is in an image that you take from a camera. You take a very large image and then you compress it down into JPEG. Well, why bother taking the large image in the first place? Why not miss out that middle large image and go all the way around it and go from a sensed environment to a compressed environment directly? And there's some great results. There's some great work being done in that area. And that has implications for some of the factorization techniques and some new factorization techniques. There's new robust methods coming out that are just quite new and do very interesting things, particularly if you're in the kind of vision circles. They do very interesting vision, sort of background subtraction and things like that. And that's all being played out very nicely with this guy in France who's got this website called Nuit Blanc, which is, he does all the factorizations, and he's got a big list of all the factorizations that go on, and he's a really smart guy, and he keeps up to date. It's a great way of keeping up to date with what's going on in that field. He just keeps it up to date for you. You just log in, there it is. So that's all being played out. The whole rank idea of SVD and the whole power and how much data I need to actually make predictions on a sort of large range is all being sort of played out, and there are actually sort of sensible little rules of, not even rules of thumb, quite sort of practical sort of terms that people are sort of playing out now. And the guy is Candes, Emmanuel Candes at Caltech. Okay, so there is this problem. So we're not without problems. We've got to choose K, and we've got to sort of know that we've got enough value in our data to get somewhere sensible. Okay, so I'm just a bit of a foot soldier. The guys that have done all the big stuff are the guys that have done, even the guy that did the iPython notebook and things like that, they're all the big guys. I'm just a workaday Python guy. These guys are the guys that are making the difference, the people who are writing scipy, numpy. It makes a huge difference to everybody else's life. So the Python community is absolutely awesome for that. It's just the best. I'm so loving not doing R anymore. It's just so much nicer. It upsets some more people. So that's it.